we're going to talk about a little bit of nothing. Okay, so if you like to talk about nothing, hey, this is the place. Now we're going to talk about gravity, okay, and how gravity has entered the picture of the universe and the picture of nothing, and the picture also of what I covered the last couple of weeks, which is not only nothing, the space, but also what's outside of nothing, what encapsulates nothing. What object can you imagine that can encapsulate nothing? Okay, so we have nothing, which we have no definition of. We have no notion of what could be encapsulating nothing, against which nothing is pushing, right? And then we have the issue of gravity itself, because, under general relativity today, we have dark matter, which is gravity pulling, right? And you have dark energy, which is trying to break it up, pushing outwards. And so you have push against pull. You have dark matter or whatever other objects are in the universe that are pulling against dark energy, which is pushing outwards. And we're going to be looking at that. What is this thingy called gravity? I mean, how does it work? That's what we got to figure out. And we'll find out that we've got more than one notion of what this really is, okay? So here, let's start with this. The fact that, like we covered the other day, we have no definition for what space is. What is space? I mean, if it's a what, how do you define the word space? That's the issue, okay? If it's a concept, define it. If it's an object, point to it. That's the bottom line. And so this is where we stand here. You have a couple of fellows, last time, tried to define space. One say, look, it's an expanse, an empty expanse, largely empty expanse. And you look up expanse, and it's an uninterrupted space. Right, so we didn't learn much. Then another fellow said it's zero-dimensional as a three-dimensional continuum, whatever that means. A zero-dimensional, three-dimensional. But the key word is continuum. You look up continuum, it's a continuous extent. And an extent is what? A bunch of space, again. So we're back to square one. We have no idea. And, these are not valid definitions. They're irrational definitions. You can't use them. And so these people pick them up primarily out of Wikipedia or dictionaries or sources like that, and they make no sense whatsoever. No one ever really defined what space is. That's where the problem starts. And here you have the space recap. What I covered the last couple of weeks. And it says mathematical physics, they only have irrational definitions, especially for space. Okay, and that's been a serious problem now for 2,500 years at least, since the days of the Greeks. Okay. And if you look it up again, space, unlimited expanse, according to dictionary.com. What's an expanse? Uninterrupted space. Or extent. They use these words, extent, expanse, and they don't know what they're saying. Continuum, again, quantitative transitions without abrupt changes. That's what it is. And you look it up, and you find out the continuum is, this 3D continuum. They find it in the Wikipedia. So again, you can't use the words expanse, extent, or continuum to define the word space, because when you look up those words, it just says it's space. We're back to square one. We don't know what space is. Our definition, that which has no shape. Now that's a crisp definition you can take to the bank. Why? It's an antonym of the other word that we need to define the word universe, which is the word object, which is that which has no shape, which is that which has shape. So we have that which has no shape against that which has shape, okay? And now we can define the word universe and say universe consists of space, that which has no shape, and matter, all those things that have shape, the bunch of them, the whole of them, okay? The aggregate of them. All objects have shape, 2D, not all objects have form, okay? So remember, we use the word shape, not the word form, because that tends to confuse people. Since all 3D forms have shape, all we need is the word shape and we're done. Okay, we cover all the bases that way. If we said an object is that which has form, well, we have a little bit of problem in English, not in Spanish or in German, for example, because they use the word form for everything. They don't have a word for shape for 2D forms, right? They only have the word form. But in English, you would have a problem because people associate the word shape with 2D and form with 3D. And so by using the word shape, you cover all the bases. We're done. Anything that has shape, is an object. Anything that doesn't is a concept, essentially. Okay. And a lot of that came from this fellow. His name is Aristotle, and they had the wrong notion. They started out with the wrong notion of what continuous means. Continuum, right? And he defined it as that which is divisible. Essentially, that's what he said. He says the continuous is divisible ad infinitum. Okay. And so if you look up his book 1 in physics from Aristotle, you'll find that in there. Okay. And today we have these notions that continuous is that which is contiguous to something. You have all these pieces, again, divisible. And that's not what it is in physics. In physics, it's that which is made of a single piece. That's what a continuous object is. We treat the table as if it's not made out of atoms. It's made out of the whole shape, it's made out of a single piece. All objects are made out of a single piece in physics. Okay. And and then they talk about continuous functions, and so that's a different notion altogether. It has nothing to do with physics. And that's the problem when they bring these notions of math and they bring them into physics. That's where we run into a lot of trouble. Okay, so that's for space. We don't know what it is, at least from mathematical physics point of view, but they use this word space, okay? And what is it? The space is simply, this extent, this thingy, whatever it is, and they treat it as a thing for all purposes, but then they tell you it's infinite at the same time. They say, space is infinite. And so if it's infinite, it's not a thing because there's no such thing that is infinite, and it can't be infinite because you have the explosion known as the Big Bang. I hate to call it an explosion. Some people will want to crucify me for saying that. It's not an explosion, Bill, okay? So this thing exploded, the singularity exploded, it expanded, whatever you want to call it, expanded, and what does it expand up against? If the singularity Big Bang, includes space and matter. It includes space. So if space is in there, what's outside of space? It's pushing against whatever's outside of space. You can't say, it's pushing against space or empty space or what surrounds it, what gives it contour is space. And they always draw this black thingy, and we don't know what that black thingy is, and it looks like space to me, And so they're only showing matter blowing up like a hand grenade, but it's always space. Inside the matter and outside the matter, it's always space. So we got a real problem there because we don't know what encapsulates space. But here we have it. It's called dark energy that's pushing everything outwards. I guess that dark energy is the space thingy that they're talking about. And so here you have it. What encapsulates space that we talked about last week. What is Big Bang pushing up against? That's the first issue you want to answer. If you can't answer that question, you can't even start your presentation because you don't have a definition. You can't even start. You haven't set the scenario, the assumptions for your theory. What is dark energy pushing against or displacing? Because if this thing is expanding, as you see it there, and you can see the whole glass, that's horizontal glass there, it's got beer in it, I think. It's a fixed shape. They always draw it as a fixed shape. And so I need to know what the black stuff that surrounds, that gives shape to that glass is, okay? And if you can't identify the black stuff, you can't even start your presentation. So this is where we don't know how to start this thing because they never answer these questions. They avoid them completely, and they say space is infinite, don't bother me anymore, So that's how they answer. Then you have the problem with the multiverse and parallel universes. They want their cake and they want to eat it as well. And here it is. They have these parallel universes, multiverses, and the question is, what's the black stuff? Okay, in the multiverse. And the other one is somewhat light blue there. What separates one universe from another? That's what we want to know because his space is inside the balls, right? Matter and space are inside the balls. That's what a universe is. What's the black stuff that separates one universe from another? And of course, they can never define it. Okay, that's the issue. They can never define what the black stuff is. They put it there, they paint it there, they illustrate it there, and nobody asks the question, what's the black stuff? And that's the key question, because if you can't identify the black stuff, you can't talk about multiverse or parallel universes. That's how simple it is. Okay, so that's the question you got to ask these guys. Then you have the string theorists, they talk about hidden dimensions. Okay, 4th, 10th, the 26th dimension. They just put it out of your reach. That's what they do. They say it's beyond comprehension, beyond your questioning. You can't even question. And so that's how they do it. They say it's infinite. It's in the 4th dimension and 5th dimension. We cannot conceptualize it. Don't ask anymore. Okay. And when all that fails, they say, well, space is infinite, and how do they explain infinity or finiteness? And here it is. Here we have our guru, good old Stephen Hawking, right? And what does he say? Well, he says the following. He says, finite, we say the universe is not infinite in space, but neither does space have any boundary. And that sounds like a contradiction. It's not only that it sounds, it is a contradiction. Okay, we have a problem there because these people run into this wall and they try to BS you saying, look, it's infinite, but it's also finite. Okay, so on the one hand, he says it's not infinite in space, meaning it's finite, right? And then he said, but it doesn't have a boundary, meaning it is infinite. But they're talking about two different things. When Hawking says this, he's saying, look, the Earth is finite because we got a surface all around, right? And what continues is space, right? That black stuff there. Okay, so we all understand that. But when they talk about the not having a boundary, unbounded as they call it, they're talking about something else. They're talking about walking incessantly around the universe or around whatever object they're referring to. So yeah, a ball is finite, but running around it is incessant because if it's a smooth ball, you don't find a fence. That's what they're saying. And these are two different notions. So to say that the universe is both finite and infinite is a contradiction because they're talking about two different, or in other words, they justify it by talking about two different things. Keep that in mind when these people talk because they pull the wool over your eyes, with it. Okay, so here we have Big Bang and we have push versus pull. We have the Big Bang there, okay, it's exploding, right? And what is all that matter pushing up against, especially including the space? Because remember, the Big Bang includes space inside it. And they call this dark energy, the stuff that's floating outwards. What we got to find out is what that is pushing up against. Because essentially what they're having is they have a push, which is the dark energy, and the pull, which is dark matter and all the visible matter. That's pulling, okay? So gravity is a pull. And you could say that anti-gravity, this dark energy, is a push. They haven't defined what this dark energy is, which is almost like 70% of the universe, right? They say it's a measure of their ignorance, and I think they came up short. I think measure of their ignorance is like 150%, okay? And so we have this in the realm of general relativity, okay? But what do we have in quantum? We have something totally different for gravity, right? They don't have dark matter or other kinds of big matter like stars and planets and galaxies pulling. They're a little more modest. They have to talk about these little subatomic things, right? And in there, they created the graviton, a particle that is supposed to pull. How you can conceptualize that, I have no idea. Here you have a ball, right? And imagine this is the particle. And I don't care how many particles of these you have. I'll give you a whole sandbox, if you want. How do you pull with this? I mean, we can all understand push. It can come up against my skin. We can say push. Okay, I understand that. Particle is pushing on my hand. Now, how does a particle pull on my hand? Now, that's tricky. Okay? Yeah, it requires a lot of imagination to prove that one. And so the way they do it mathematically. And here it is. Here's the mechanism, okay? This is not gravity, but it's the same action at a distance mechanism, okay? And here you have the gluons pulling on quarks. This is the way it works, okay? You want to pull out a quark? Well, you send a gluon, and somehow it creates what is known as negative momentum transfer, okay? It throws a particle and it pulls the other quark in. And you can imagine those two quarks as objects, as two particles or two planets, whatever you want to put in there, it doesn't matter. What they're saying is you're sending these particles outwards, like the gluon there. You're sending the particles out, the graviton, okay? And somehow it pulls the other object inwards. And we can illustrate it, but it's unimaginable how this thing works in real life. Okay, you cannot imagine. And so, yeah, we're dead. We're stuck here because we cannot get beyond it. This is an irrational mechanism, and they just illustrate and say, "Look, it is so. Please believe us because that's what we proved in the lab." And take it or leave it. But even if we concede it, let's concede it. Let's go out of our way and concede it. What does that have to do with this, dark energy that's pushing everything outwards, and you have the pull of gravity, matter, and dark matter, and all this other, and black holes and so on, wormhole. All this stuff is pulling stuff inwards. So, okay, so one is gravitons. The other guy is, mass that's pulling on dark energy, on whatever's pushing us outwards. They're two different mechanisms. Both of them are, you cannot imagine them, and they don't try to imagine them. They just say it is so. And so you have to believe on the basis of faith. Okay, that's how it works. And so we have a gentleman, his name is Arvin Ash, and he's going to illustrate for us what the mechanism of quantum gravity is, this graviton thingy. And the way he does it, and the way we're all moving in quantum mechanics, is we're abandoning quantum. We brought the word mechanics and forgot about the word quantum, okay? Because now they're going to have a field. It's a field day, right? And what is a field? Well, the field is whatever. It's a bunch of numbers. That's what a field is. It's reduced in strength as you get farther away from ground zero. Okay, so you whatever point you pick, you have all these numbers, these values, and they get weaker and weaker the farther away you get from that point. That's what a field is in mathematics. Faraday saw it as a region where something happens that he could not identify. And so they kind of mix these two together and say, well, it's a field, and there's a region, and we have all these values in there, and they treat it as a physical object. Somehow the math becomes physics. That's where the problem is. And so what this fellow Arvin is going to say, look, we have these fields, and we're going to exchange a graviton. Exchange a graviton. How do you do that? And let me tell you what the first problem is. The first problem is that he says that a particle is a vibration of the field, a local vibration of the field. So if you have the field, whatever the field is, all these numbers, right? They're vibrating, but locally they vibrate and they create these little peninsulas. They're not islands like a ball. This is an island. It's completely surrounded all around by air and ultimately by space. That's not what they're talking about. They're talking about a peninsula. It's a protrusion out of the field, local vibration of the field, but it's still stuck to the field, so it's a peninsula and not an island. Keep that in mind. But somehow he's going to get a little particle that floats between two fields. He's going to call it a graviton. I don't know how he got loose from its field. That's one issue. The other issue, he's going to liken it to a photon. And he says a photon is the one that mediates the electromagnetic attraction. Okay? And so an exchange of photons, little particles, discrete particles, which is also part of a field apparently, an exchange of photons brings two things together that are of opposite charges. Well, there's no such thing as opposite charges in mass, in the fields that he's going to bring together. We're not talking about charges here. It's just they all have the same charge, but somehow he's going to send this graviton back and forth or forward, and somehow that brings the two objects together. He doesn't explain the mechanism. But listen to him. It's a lot of fun just listening to these guys because they think they know something about something and they know nothing about nothing. And here it is.
One can attempt to treat gravity as a field analogous to the electromagnetic field. An excitation in this gravitational field would be the graviton, just like an excitation in the electromagnetic field is the photon. The exchange of gravitons between two particles would result in attraction. This is analogous to the way an exchange of photons results in electromagnetic attraction between two oppositely charged particles.
So, did you understand the mechanism? Can you repeat it to me? How does the graviton do it? See, in the case of the electromagnetic fields, right? They have this photon going back and forth. One's positive, the other one's negative. But that's not what he said for the masses. He said there's an exchange of graviton, and it's kind of like, the photon. That's it. So I don't know how he does it even with a photon, let alone the graviton. Okay, so that's the gravity version of quantum mechanics. Now you know it all. Now you can get your diploma as soon as you pass the test on Friday. Okay, how do we do it in general relativity? Well, a little differently here. This is the version of general relativity. What they have is warp number lines, okay? All those lines that you see there, right, the green ones, those are number lines. They're not even dimensions or coordinates or vectors. What they are is number lines. And they're bending the number lines. Why? Because they're talking math. They're not talking physics, but they turn their math into physics, and they say, we're going to bend the number lines. That explains why the Earth there, the little guy there, right, little ball, doesn't fly out of the solar system. It's caught in this depression like, a ball rolling around a funnel, right? And it doesn't fly away. That's the mechanism. So we have these two mechanisms. One's the graviton that brings two fields together, fields of mass, I guess. And then we have the warp number line version. Okay, so you take your pick, which one you like most. And so just in case we ask one of the celebrities that we have today, which is Neil Tyson deGrasse. Good old deGrasse is going to tell us what gravity is. So listen carefully to his explanation for the gravity that involves general relativity. Here it is, okay? Listen.
Science can describe how gravity works, but can they describe why it works? So this is the how-why duality here. In science, if we can describe how something works and predict its future behavior, we claim to understand it and we move on. There's a point where it's not especially productive to continue to think about the world that way. When you understand the how enough, are tantamount to having answered the why question. I can describe what gravity is doing. I even have a mechanism for it. Gravity really is the curvature of space and time. Movement of matter on that fabric of space and time we call gravity. Why does matter and energy curve the fabric of space and time? And I don't have an answer for that. Why does matter and energy curve space and time? Okay, that's a frontier. We're still working on that.
Yeah, they've been working on that for 2,500 years at least. They're still working on it, okay? So, what's the issue? The issue is that we don't know why this spoon, right, falls to the ground. Okay, why it falls downwards. But they're working on it. I mean, it's so complicated, what do we have here? A spoon and the earth, essentially, right? And it falls downwards, and no one can explain the mechanism. And so the question is, how many more centuries, how many more thousands of years do we need to answer that simple question? And after saying all that, good old Neil says something else. He kind of gives us the punchline. This is from his show, which is Star Talk. And listen to him. Here he's going to tell us the punchline. Okay, listen carefully.
We can describe gravity. We can say what it does to other things. We can measure it, predict with it. But when you start asking, what it is, I don't know. I don't know. I don't know. I don't know. What it is, I don't know.
So there you have an answer. They don't know. They don't know. I don't know. I don't know. That's the answer. That's how, first they tell you they know, it's the warping of space, then they say, I don't know. Okay, what is it that we need to answer regarding gravity? Very simple. I mean, here I told you, right? You have to tell me what causes the spoon to fall to the floor. Very difficult thing, Jesus. Just a little spoon in the earth. That's all it is, and it goes down, and nobody can answer that question. How can it be so difficult? Well, here, let's get another professor. He's from Berkeley, and he's going to give us the specification, what you need to understand, what you need to answer. Okay, he's going to tell you what we need to answer regarding gravity. Here it is. Listen carefully.
If you have the Earth with its big mass here, and you have you with your little mass here, that every atom on the Earth is pulling on every atom of you. You're also pulling on it. You're pulling on atoms right now on the other side of the Earth. On the other hand, there are a lot of atoms here you're pulling on. You're pulling on all of them. The amazing thing about gravity is it goes right through things.
So what is gravity, or what is the specification? What is it that we have to answer? We have to answer how every atom, right? Every atom of the spoon is pulling on every atom of the Earth. That's what we have to show, okay? That's what we have to explain, how that's possible. Well, the only way it's possible is if every atom on the spoon is connected to every atom on the Earth, then every atom on the Earth can pull on every atom of the spoon, and every atom of the spoon can pull on every atom of the Earth. Okay, very simple stuff, really. Means that every atom of the universe has to be physically connected to every atom of the Earth and vice versa. That's what it means. That's the only way you can explain that. And the only way it can be connected is through some kind of elongated object. You know, for example, a rope, right? Not as big as this one. No, it's got to be something unimaginably thin, and it's long. It stretches from one atom of the spoon to one atom of the Earth. You take your pick, whichever atom you want, okay? And so here's a summary of what good old Professor Muller talked about. Says again, what you have to explain is how one atom can pull on another atom. And the only way you can answer that is with an elongated object. There you have the link at the bottom. Just look it up and you'll find his own words there, okay? There's the YouTube video. Okay, so we need an elongated object connecting any two atoms to talk about gravity. Period. We're done. That's it. No warp space, no graviton flying back and forth, none of that. Okay, so how do we explain it? Well, here it is. This is the assumption. And once you have the assumption, it all falls in place. It's very easy. There it is. All the atoms in the universe are physically connected on the upper right. Okay, there. And we say that those lines that you see there connecting every little dot, you can think of them as galaxies. You can think of them as atoms. It doesn't really matter. We're saying that it looks like what you see at the bottom left, which is two atoms connected by a rope-like entity. That's the architecture of what connects two atoms. And now, yeah, we can talk about pull. We can talk about tension. We can talk about a lot of stuff that doesn't involve push. Okay? What we have there is connection, physical connection. Now we can explain gravity very easily. We don't need to talk about particles flying back and forth, and we don't need to talk about, dark energy pushing against the pull of dark matter or any nonsense of that nature. Okay, so that's the issue. The issue is that once you connect all the dots, you're done. That's it. That's all we needed to figure out, that there are invisible, intangible mediators, elongated mediators that connect every atom. We're done. That's how simple it is. Okay, and now, yeah, we can explain gravity very easily. Here's an astronaut flying to Earth. I've shown this several times. Let's show it one more time. As he falls, all these interconnections, these physical interconnections, they fan out. Okay, so they're not on the same axis. You can imagine this astronaut at infinity, far, far away from the Earth. All those what we call ropes, electromagnetic ropes, come together and form a single axis, a single coaxial. And as he approaches the Earth, they all fan out, and that explains the acceleration of gravity. Why you fall faster and faster and faster the closer you are to the center of a celestial object. Okay, so we're done. We can explain gravity with these ropes because the only issue here is that you cannot see or touch them. They are invisible, intangible, and that's what threw everybody off throughout the centuries. Okay, so the other issue that we need to answer, and that is that, gravity goes through things. You can't protect yourself against gravity. If you're falling from an airplane, you can't open your umbrella below you and say, oh, the umbrella is going to protect me. No, the umbrella is going to fall together with you. Okay, you cannot put a shield or something below you and say, I'm protected against gravity. No such monster. Why? Because gravity goes right through things, as Mr. Muller said. The funny thing, the strange thing about gravity is it goes right through things, meaning it goes right through an atom. Whatever you postulate, whatever your assumption is, it has to go through the atoms, okay? So the atom behind another atom, gravity goes right through them. That's what you got to explain. The only way you can explain that is if these connectors, these elongated physical mediators, they are, attached to all these atoms, and they go right through them, right? And here's I'm going to try to illustrate this. Here it is, okay? Here you have these atoms on the left, 1, 2, 3, 4, 5, 6, 7, 8. And 3 of them belong to the sun, 2 of them to the earth, and 3 to the moon, okay? Now, let's say they're aligned, okay? They're on the same axis for a split second, of a gazillionth of a second, right? And they're all on the same axis, okay? So when they're on the same axis, the only thing that, for this set, the pull is only between atom 1 and 8. That's it. All the others, 2, 3, 4, 5, 6, and 7, they don't exist as far as the universe is concerned for that axis, okay? So you have just a tug of war between 1 and 8. There's a tension between those two, momentarily, Now, as the Earth passes, for example, right, which is the frames on the right there, you can see that number 4 and 5 are not on the same axis anymore. Now, for the first time, those two atoms are noticed by the 1, 2, and 3, and 6, 7, and 8. Suddenly, it's like this, like a rubber band, right? You can pull on it, and all you feel is your fingers. You feel the tension there. You feel some kind of pull, right? But what happens? You ask someone to hold the middle, just to hold it, not to do anything, not to pull, because he can't pull on both fingers at the same time. He can't pull on the left finger at the same time as he pulls on the right finger. He pulls on one or the other. He can't pull on both. So if he just holds it, right? If he just holds it, that you won't feel that person. These two fingers won't feel that person. They will continue to feel each finger. That's it. That's all they will feel. They won't feel the fingers of the person who just touched that. But what happens when you pull it out of alignment? Okay? Now, these two fingers, this one and this one, right? The center fingers, they will feel the pull of the person pulling on the thumb, right? Because now they're not on the same axis. And that's what I'm illustrating there. I'm saying that, gravity works like that. Mass works like that. You're only going to feel the mass, right? If the atoms go out of alignment, go out of that axis. And that explains gravity in a nutshell, right? We do have a mechanism. It was baby stuff, kid stuff. The only issue, the only one that stumped all these mathematicians for hundreds and thousands of years is that they cannot see or touch the mediators, the elongated mediators.